So we haven't talked a lot about the radian value. I showed you guys briefly of what the radian stuff comes from. The radian value are, you know how the rest of the world uses metric system?
Yeah.
Well, radian is kind of like the standard form for a lot of trigonometry. We still use degrees. Degrees are used lesser throughout the world. They still use degrees, obviously, for bearings and stuff like that, because it's easier to measure with normal devices as opposed to a radian. But pure calculation stuff is usually done within a radian value. A radian is, like we showed yesterday, when you have your XY grid, your two-dimensional Cartesian plane, if you will, fancy words today. We start at 0, 180 to 360. In reference to that with a radian, it's built into a circle. It comes from, obviously, a standard value of a radius. The radius of the circle doesn't change. Okay? The radius of the circle won't change when it's placed at the origin. It just rotates all the way around. So it comes from circumference in circles, and that's why there's a pi in it. And we just convert it out as 0, pi, and 2 pi. 90 degrees then, if 180 is pi, 90 is half of it, so what do you think that is in terms of radians? Half pi. What do you think 45 degrees would be? Quarter pi. Okay. This is 1.5 pi, so it's 3 pi over 2, and so on. What we usually do is that we will eventually build what you guys might have seen before. It's called the unit circle. The unit circle is built off of the two special right triangles and the quadrantals. The quadrantals are your multiples of 90. Pi over 2, pi, 3 pi over 2, and 2 pi. Things like that. So they're built off of that. What we do is we go through and do conversions of degrees to radians within those values, because you'll notice really fast the fractions are very easy to work with. These are the only ones you really have to worry about. I don't know if we'll do that so much today, but we'll probably get to more of that tomorrow. We might as well do it today, doesn't hurt anything. So let's do this. We talked about degrees to radians. To do degrees to radians, you take your degree, divide it by 180, and slap a pi next to it. To go the other direction, it's just the inverse. So you take the radian, divide it by pi, and then multiply it by 100. Okay. Very, very easy to go in between the two. Very simple to go between the two. What I want to do is take something that we know, our two special triangles, and convert those angles. And we've talked about these side lengths a bunch of times, right? 1, root 3, and 2. 1, 1, root 2 for the other one. We've done all that. Okay. So what I want to do is I want to take a little bit of space. You might want to use I'd use, I don't know, maybe 4x4 little section of paper, and we're going to create, and we're going to make our stuff go around. We'll show you what the rest of the world does with this. We're going to build a unit circle. Okay. We're going to build it. And it's, like I said, it's built out of, it's pretty close on my ankle bothers. Too shabby. So here's what I want to do. I want to take 30 degrees and convert it to radians. 30 degrees going to radians, remember degree over 180 and slap pi on there. So 30 over 180 is 3 over 18, which is 1/6. So 30 would be pi over 6. You could write it as 1/6 pi if you'd like. I would suggest just to leave the pi in the numerator. It's just easier to write. Okay? And it'll be easier to use some quick calculations and stuff later on too. Okay? Now, conversely, do the 60 degree right away then. You do 60 degree, 6 over 18 is a third, so it would be pi over 3. The reason why I wanted to show you those two right away is that notice the 6 in the denominator goes with the 30, the 3 in the denominator goes with the 60. They flip to each other. Okay? That's why. It's one thing, it's one way to kind of think about it. Plus, isn't 1/6 plus 1/6 equal to 1/3? 30 degrees is twice as much as, or sorry, 60 degrees is twice as much as 30 degrees. So it's a lot of little things that happen. Go back to the 45 then. We already said this. We know that 90 degrees was pi over 2, right? So then, what's half of a half? A fourth. So at 45 degrees, it's pi over 4. So we have 0, pi over 2, pi, and 3 pi over 2. And it comes back to 2 pi. So here's where things get interesting. As we come through the other side, sometimes it's easier on students to build the third quadrant next, because if I continue this line through here, and then this one through here, in essence, what am I doing to that pi over 6? What am I adding to it? Pi. I'm just adding pi to it because it's just moving 180 degrees across. Because this line is straight across from it. If you tilt your head, this is just moving itself over 180 degrees because of what's called that reference angle, down 30 degrees from 180. Well, 180 plus 30 is 210. Oops, can't write. So we have 210. And what's 1 pi plus pi over 6? 7 pi over 6. Same deal. 45 degrees more than 180 would be 225. And what's 1 plus a fourth? 5 pi over, it would be 5 pi over 4. And the same thing with the pi over 3. 60 degrees more than 180 would be 240. Yeah. And then pi plus pi over 3 would be 4 pi over 3. And like I said, the reason why I like to build them across from one another, because you're just adding pi to it. You'll notice that each one of these is 1 and 1/6, 1 and 1/4, 1 and 1/3. Yes, ma'am. This one here, it's 180 plus 60 is 240.
You said the numbers, but I was thinking of different numbers, so, and I was like...
And I love the fact when people think, you know what they always do? They look up to their brain. Brain, don't fail me now. It's always funny. Okay. Does that make sense about going into just why I like to just bounce between 1 and 3? It's pretty quick. Okay. So now it comes into the idea of the next set of angles. Well, it's not that funny. The next set of angles. Well, the easiest one to do is the 45-degree angle. What's 45 degrees more than 90? 135. Okay. What's a fourth more than a half? 3/4. Okay. Now it comes into the idea that I've been showing you guys a lot. Notice how I've been walking you guys through the idea of coordinates not changing. Remember I've been talking about how the signs, SIGNs, change as they come across? This angle here has the same reference angle as this one. This is going to be 30 degrees off the x-axis, up. What's 30 degrees up from the x-axis? 150. If I went up 30 degrees, that means I went up 1/6. What's 1/6 less than a whole? So it's 5 pi over 6. Pretty easy to build, isn't it? By bouncing things back and forth, this is relatively straightforward. Same deal with the 60-degree reference angle. Going up 60 degrees from 180 is how much? 120, good. What is 1/3 of a whole? Take out a third from the whole. 2/3. You came up a third. Here? It's 150, it's rotating. This is terminal side, so it's coming 150 around.
No,
The-
I'm just confused with angles. You already wrote 135 up an angle.
I think you guys skipped a line on that.
Yeah, you skipped a line.
It goes 150 and then a line.
No, the 150.
Oh, I put the 135 above it. It doesn't matter really where.
Yeah.
It could have been either spot, really.
Inconsistent pattern.
Sorry. Sue me. No. Again, what I'm doing here, guys, is I'm using the acute angle in the first quadrant to bounce it up on the other off the other axis, because that's how they share their same ordered paired endpoints as we continue to build out stuff. Okay. And another easy thing to do here is if you want to rotate it through, what are you doing to each one of these angles then? Each one of these, you're just adding 180 to bring it to the fourth quadrant. So each one of these fractions, you're adding a whole to drop them through. Okay. So if I start with the 150, that gives me, add 180 to that, what is that, 330? Add a pi to 5/6, you get 11/6. And again, notice, it is 1/6 off the x-axis. It shares that exact same reference angle of the acute angle within the first quadrant. 135 into the fourth quadrant. 240, no, 235? No, that was
I
that
don't think
one.
that's right.
315, sorry. Math is hard.
That's it.
And then I get 7 pi over 4.
Oh, okay. Now I got it.
It's 1/4 off of the x-axis. Bless you. And 180 and 120 is 300. Add the whole to it, we get 5 pi over 3.
Where are you getting the text?
How am I getting them? I'm taking this 2/3, I'm adding 1 pi to it. I'm adding 3/3. 2/3 plus 3/3, 5/3. 3/4 plus 4/4, 7/4. 5/6, 6/6, 11/6. Or, if you want to go the other way, if this is 2 pi here, this would be 12/6, subtract 1. This would be 8/4, subtract 1. This would be 6/3, subtract 1. That's the whole point of building those through.
Did you write the angles the same way?
Sure. What do you mean?
Is like the 330 supposed to be?
330s for this one, 315, 300, 240, 225, 210. Well, yeah, because that's the terminal side as it comes around to here.
Oh.
Okay.
Got it.
The fun part begins then when we start to think about sines and cosines. Remember when we talked, let me just show you this and I'll leave it at this then. If this is the 30 degrees, if I drop a vertical to the x-axis, I just took out the sector. Bless you. I took out the sector. You guys remember what a sector was?
Nope.
It's the
Kind of.
piece of pizza, pie cut pizza.
Okay, yeah.
All right. I took out that chunk, so it still has that radius to it, but I dropped the vertical to the x-axis. That creates the right angle. Okay. That creates a 30, 60, 90 triangle. Opposite the 30 and the 30, 60, 90 is your 1. Opposite the 60 is the root 3. And opposite the 90 is the 2. Which means if I'm looking at my x and y values, I can get my cosines, I can get my sines from it. Remember, your cosine is your adjacent over the hypotenuse. Your sine is your opposite of the hypotenuse. What you're able to build here is that this point has a horizontal value of the cosine, and it has a y value of its sine. So as we go through our ordered pairs, we're going to be able to take that ordered pair, rotate it to this quadrant here. It's the same ordered pair, but what changes? The x becomes negative. Here, they're both negative. Their y is just negative. So this entire unit circle that we spend so much time on is really only developed off the acute angles in the first quadrant of your special triangles.
We should learn this before we do the triangles with the extra angles.
Well, you don't have to worry, you know, and there are times that I start thinking about not doing it that way, and maybe next year I won't do it the way I've been doing it the past few years, because you're right, it is nice to see why things can bounce around, but it's really not really needed to know the full on to it, because I like to break this into calculator, non-calculator, and I think that stuff is okay, and I can kind of fudge my way through showing you guys why it kind of works. And then as we get to the non-calculator, really show you why it does work. I don't know. But you're right, it is. Next year I'll do it. I'll screw somebody else up. So that's where, and I'm going to get you guys a copy of this. It's a really cool diagram one that we'll build. I have been known to ask for a quadrant every once in a while. Yeah, that was nice. Oh, it's very nicely done to do. This is what we just built, blah, 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 gradients, this thing. Area of a sector. You can use area of sector with arc length, arc length and area of sector can be found via radians as well. If you guys remember arc length, in geometry, you guys did central angle over 360 times 2 pi r. Remember that?
No.
That was your arc length?
I can't remember.
I
Well,
remember it.
Watch what
I was
happens.
gonna agree with you.
2 goes into 360 how many times? So you get angle over 180 times pi times r.
Yeah.
Isn't this angle in degrees converted to radians? Isn't it just radians times radius is your arc length?
Wow. We do that arc.
Wait, what's that back?
That's how you get arc length, yeah.
So
Arc length is your radian measure, this theta. It's just degrees converted to radians times your radius. Well, that would have been nice to know last year.
Yeah, it would.
But here's the thing, last year you guys in geometry, you didn't need to worry about radian measure. You didn't need to know it yet. I know, Seb's just a jerk. And then it works the same way when you try to find the area of the sector. The area of the sector, you had to do central angle over 360 times 2 pi r squared. Well, if you simplify that out, you're just getting r squared times theta times a half. It works the same way. This theta value is just the converted degrees into radians. That's all that is. It's a very easy formula to work with. So you'll be given a specific degree measure and a radius. It's going to ask you to find the arc length. That's it. So if I have a degree measure of 135 and a radius of 6, all I do is I convert that 135 into radian. 135 over 180, slap a pi next to it, and multiply it by 6.
That's it.
And that's it.
Sweet.
Sure. If I have the same value with the, I want to find the area of it. Let me move this up a bit. It's 1/2 radius squared times theta. Well, I take my 135 over 180 times a half times 6 squared. Oh, forgot my pi. It's quite literally that fast. You don't need one.
that's
No. What's 180 times 2?
360.
What's 6 squared?
36.
So you have 135 pi times 36 all over 360.
That's it.
What happens?
The 3 and the
This drops, 36 goes into 360 how many times? 10. Okay. So you have 135 pi over 10. What can you divide them both by? 5. So let's see. Was it 2? What is it? 25 pi over 2? No, not 25.
No, not 25.
27. 27 pi. You don't need a calculator.
You just got it wrong.
No. There's no such thing as a decimal.
You just got it wrong.
That's like the quickest way to make it.
Hey, same thing you guys did yesterday. Do the radian ones from yesterday, and also do the next 6 of the central the arc length and area of sector.
Wait, what numbers?
So it'll be 60 through 65. Do 6 of those as well. Okay. So you're gonna do all the radian ones from the same numbers from yesterday. Obviously, let me change that. I think it went to 59 for that last group. So let me see here.
So 28 through 59.
Trying to find the homework. Yeah, so now it's 28 through, now it's radian stuff.
Your
So
51
rad.
stuff.
Yeah, but then remember it jumps. It'll be 28 through 43, it'll be 52 to 65. So 43, we change this to, and then 52, 65. So this stuff and this stuff. Okay? Try to stay off the calculator. Your rambunctious, you want to look at the problems towards the end there. It says evaluate the 6 trig functions at specific pi values. That's kind of where all this is headed. So if I want to see what are all the trig functions at pi over 6, well, that means what's the sine, cosine, tangent, and all that at 30 degrees. Oh, radians, you're so cool.